sharpness of resonance or Q factor. Students, see a graph. I have plotted a graph between current and frequency. Current is considered on y-axis and frequency on x-axis. For different values of resistances, we get this type of graph. I have plotted 3 graphs for 3 different values of resistance. Now, the graph shows the variation of current amplitude, that is I0, current amplitude I0, maximum displacement covered by the vibrating particle, vibrating body from its mean position. That's why it is maximum value of current or peak value, or we can say current amplitude. Okay, now you see the graph shows the variation of current amplitude in a series LCR circuit with angular frequency omega for 3 different values of R. See, I0. I0 has a peak value of resonant frequency, that is omega R. Omega R, R for resonant. That's why for resonant frequency we can write omega R. Omega R is equal to 1 upon square root of LC and falls to 0 in either direction. See, 0 in either direction. The resonant frequency is independent of R, but the sharpness, resonant frequency is independent of R, but the sharpness, you see the sharpness of peak depends on R. The peak is higher. The peak is higher for a smaller value of R. See, the peak is higher for smaller value of R. Thus, the resonance is sharp for small r and a flat, you see third one, a flat, almost flat, and a flat one for large R, higher value of R. The sharpness of resonance is measured by a coefficient called the quality or Q factor. Quality or Q factor of the circuit. See, the Q factor of a series LCR circuit is defined as the ratio of the resonant frequency to the difference in two frequencies taken on both sides of the resonant frequency, such that at each frequency the current amplitude becomes 1 upon square root 2 times the value at resonant frequency. Mathematically, we can write Q factor. Mathematically, Q factor can be written as Q for Q factor. Q is equal to omega R upon omega t, omega 2 minus omega 1. Okay, omega R divided by omega 2 minus omega 1. See, Q can be written as omega R resonant frequency or difference between two frequencies. Here we can write 2 del omega, or Q is equal to resonant frequency upon band width. Students, see one graph. Graph is plotted between current and omega, and the graph shows bandwidth of a series LCR circuit. Bandwidth of a series LCR circuit. Now see the graph. I, current, is considered on y-axis, and on x-axis we can take omega. So we have this type of graph. Okay, see, it is bandwidth. This one is bandwidth. Here omega 1 and omega 2 are two frequencies at which the current falls to 1 upon root 2 times its resonant value. Here omega 1 is equal to omega r minus del omega, and omega 2 is equal to omega r plus del omega. The frequency range omega 2 minus omega 1 is equal to 2 del omega, frequency range, and this frequency range is called bandwidth. Here you see, it is called bandwidth. Okay, the larger the value of Q factor, the smaller is the value of bandwidth. See, larger the value of Q factor, smaller is the value of bandwidth. Q factor is dimensionless quantity as it is a ratio. Now, we have two expressions for Q factor. One is Q is equal to omega r L upon R. Equation A. Second one is Q is equal to 1 upon R into square root of L upon C. The equation is named as B. Now consider this one, this expression. Q is equal to omega R L upon R. Equation A shows that if Q factor is large, that is, if R is small or L is large, the bandwidth is small. This means that the resonance is sharp, or the series resonant circuit is more selective. Now we will see the use of this series resonant circuit. A series resonant circuit can be used in the tuning of radio receiver.